Welcome to lesson 56, exponential growth and decay. So in other words, exponents that make numbers go bigger and smaller. So as we're modeling today and as you're practicing today, be sure you're working on these things and making them noticeable in your work. Identifying when a situation represents growth or decay. We want to make that very clear in our work. How we actually read the question carefully and use the keywords to find the initial value of the situation and express the rate as a decimal. This is just like in middle school where we did percent change. Anytime it was a percent increase or decrease, we wrote it as a decimal. Plus 100%, we just wrote 1.00 if it was added, or we subtracted from 1 if it was a decrease. And we're going to use these two pieces of information to form an exponential function. And finally, we're going to apply that function to answer any contextual questions. Let's take a look at these notes. So pretty much this is the formula we're going to use again and again and again. So far we've seen exponential functions written as y equals ab to the x power, where a is the original amount and b is that constant ratio, what's being changed over time, whether it's a decrease or an increase. So it works really well if you're talking about halving or doubling or tripling. But sometimes something grows or decreases by a constant percentage. So that means we have to show it another way, and we're going to use exponential growth or exponential decay to represent this as a function. So let's look at what that function looks like. You'll notice, here we go, our final amount is equal to our A, original amount, 1 plus or minus that rate. So obviously if it's an increase, we add the rate. If it's a decrease, we subtract the rate. But the rate has to be written as a decimal. And then this is to time in years. So that's going to be our exponent. So let's say something it decreases 5% every year. Then we would write that as 0.95 to the number of years. Okay, so whatever the original amount is, A times 0.95 to the whatever number of years in exponent. So that is a 5% decrease. If something has a 15% increase, we would add that to 1, and it will be 1.15, and then to time. And that's how we would figure out the final amount once we have our other unknown, which is the amount and number of years. Let's try writing out that function. A painting is increasing in value at a rate of 12% per year, and its value in 2010 was $1,500. All right, so let's write that exponential function. So y equals, our original part is a, 1 plus or minus the rate to time. So we already know what the original amount was, $1,500. We know it's increasing by 12%, so 1.12. And then however many years in time, we'll put t for time. Now, in the second part, let's find the values, the painting's value in 2016. All right, so we also know this was 2010. So I would do y is equal to 1,500. Here's my rate, a 12% increase, and this is 6 years. Let's hit pause so we can get our calculator out. I want to show the slight difference when I do this as a two-step using order of operations versus one step on my calculator. So I'm going to do 1 and 1200ths to the 6th power. There we go. And I get 1.973. So I'm going to multiply that by 1,500. And I get the final cost of the painting at $2,959.50. Now I want to compare this to if I wrote this down as one entire expression in my calculator. So 1,500 times 1.12 to the 6th power. And you can see it is just slightly different, ever so slightly different. $2,960.70. I'm going to round it to 73 cents. So it's a difference of only $1.23, but that's only from the rounding that happened with the exponent. So I just want you to take note of that and recognize that, and that may happen in your work when you're doing it as two separate steps, because you're going to end up with irrational numbers like you're going to end up with non-terminating decimals for many of these, and you want to make sure that as you're writing them down, you'll often cut them off or round them to the nearest thousands, and how that small change can have a slight impact on your final answer. Try the next one on your own. The shark population in the ocean is decreasing at a rate of 5.2% per year. The original shark population was 68,000. Write an exponential function to model this situation and find the population after 5 years. Hit pause, solve the problem, and then unpause for the reveal. And here is your reveal in 3, 2, 1. Here is your formula. Your original amount, 68,000 times 0.948. So that is a decrease of 5.2% to the t power. And based on, depending on how you solved it, you probably got 52,066 sharks or 52,020 sharks. Oops. And that again depends on whether or not you wrote the entire function into your calculator or if you did it in pieces. So for example, if you wrote, here's my calculator, 6800 times 0.948 to the fifth power, then you would get 52,065.5. So I just rounded up to 56. So this is if you wrote it all just in one on your calculator. But if you did your order of ops and did your 0.948 to the fifth power first, then you would get 0.765 and then multiply that by 68,000 and you would get the second answer. Okay, and that's basically it, Math Marbles. So that's what you're looking for today. You're going to be able to just recognize, is it a growth or is it a decay? And depending on that answer, that's how you're going to change your function. You're either going to add the percentage to 100 or subtract it from 100 and write it as a decimal. And then use that to answer any of the questions in your work sample. All right, I hope this is really helpful. I will see you in the next lesson. Be well.